All right. Hello, everyone. Today is March 22nd, Monday, fourth week of the spring semester. Now it's late March. First of all, I hope you guys had a great weekend and enjoy the weather outside today. It was simply terrific. Uh, and I stopped by the community center of my apartment for recording lecture videos. Unfortunately, I couldn't start yet till now. Now it's almost midnight because I distracted so many things, distracted by so many things. So it was not my day, but will do my best uploading a couple of videos at least before I go to bed so that you can watch and study from Tuesday morning. So in this first video, I'm going to finish the lecture slide previous week because I couldn't finish that due to lack of time. In the last video, I explained how to compute the determinant of matrices, and so let me quickly finish this slide. So for 1 by 1 matrix, determinant is itself, and 2 by 2, we have a nice formula, and 3 by 3, we used minor and cofactor to express the determinant as a linear combination. Okay? And let me remind you of this two-stage procedure. So at the first stage, for computation of the determinant of 3 by 3, and we need to choose one row or one column in that matrix. And if we choose row I, then determinant A is going to be linear combination between the entries in that row and corresponding cofactors. And if we choose column J instead, then determinant of A is going to be linear combination between the entries in that column J and the corresponding cofactors. Okay. Of course, row I does not have to be the same as column J, but nevertheless, we are going to get the same expression, same value of the determinant. Okay, so that is a remarkable thing, and this fact comes from the one major property of the determinant, and we are going to study several properties of a determinant, but not this. So you may wonder why we end up with the same value of the determinant independent of our choice at the first stage. But unfortunately, it is beyond our scope. The exact proof is way more complicated than you had expected. So for the exact proof, you may have to go to math department to take advanced class, but this is just the elementary class. I don't think we have to know everything about linear algebra. So let me skip the proof about this. Okay. So we are going to take this as a fact, and we are going to make use this fact and to investigate several applications by computing the determinant of matrices. Right? So I did do these two examples in the previous video, but the previous video was cut off for no good reason. So let me redo this example, the second example, matrix B. So matrix B is right here, is a 3 by 3. And once again, the two-stage procedure begins with one choice of column or row. Okay. But for this example, let me choose column 1 because it has a number 1 and number 0. Okay. So I think that's the best choice in this example. Okay. Then matrix B is going to be linear combination between the entries in the column, so 1, 8, 0, and the corresponding cofactors, C sub 1, 1, C sub 2, 1, and C sub 3, 1. So it's going to be, determinant is going to be the sum of these three components. And remember, when we express matrices, okay, the first subscript is a row, and the second subscript is used for column. Okay, so for example, corresponding cofactor to number 8. Number 8 is in the second row and first column. So corresponding cofactor is going to be C sub 2, 1. Okay, and to 0, cofactor is going to be C sub 3, 1. But we don't have to care about this because multiplied by 0, so it goes away. And the C sub 1, 1, the first cofactor is, after elimination of first row and first column, we are left with this 2 by 2, and that determinant, so whose determinant is 77 plus 8, so 85, right? And C sub 2, 1. Now eliminating the second row and the first column, then we are left with this 2 by 2, 1, 4, 4, 7, and whose determinant is 7 minus 16. But remember, we shouldn't forget the sign operator negative 1 to the power 2 plus 1 in the definition of cofactor. Okay? And remember, the cofactor is a signed minor. Minor is just the determinant of some matrix, but cofactor is a signed minor, so signed determinant of some matrix. Okay? And for C sub 2, 1, because the sum of the subscripts is a odd number, so we have to change the sign to negative. Okay? For C sub 1, 1, we don't have to consider this sign operator because the sum of the subscript is even number, so it does not change the sign. It remains positive. Anyhow, C sub 2, 1 is therefore number 9. Okay? So the determinant of a matrix B is 85 plus 8 times 9. So I think this is a 3-digit number. 157, I guess. So hopefully my computation is correct. But if you found something wrong, please tell me at the live lecture this Friday. Okay? So in this example, in order to evaluate the determinant of this matrix, I use the first column, okay, and compute the linear combination of this first column. And this linear combination is called a Laplace expansion by the first column of matrix. Let me write down here. So this is called a Laplace expansion by the first column of matrix B. Okay, so it's named after one of the greatest mathematicians, Laplace. I forgot his first name, but this Laplace expansion helps us compute the determinant of any scalar matrices. So here we computed 3 by 3 matrices determinant using Laplace expansion, but it can be extended to any scalar matrix regardless of dimension. So in the next slide, we have a 4 by 4 example. So here 4 by 4, and in order to compute the determinant, the procedure is exactly the same as before. Okay, so we begin by choosing one column. For this matrix, let me choose the third column because this column has the largest number of zeros. It has 3 zeros, so greatly simplifying our computation work. Okay? And call this matrix A. Then A's determinant is just a single term, 4 times C sub 2, 3. Because the only non-zero number, the only non-zero entry number 4, that shows up in the second row and in the third column. Okay. So the corresponding cofactor is a C sub 2, 3, right? But this cofactor, in contrast with a previous example, because after elimination of the second row and the third column, now we are left with a 3 by 3 matrix. Okay, so C sub 2, 3 is a negative 1 to the power 2 plus 3 times determinant of this submatrix. Now this is a 3 by 3 matrix. Okay, so unfortunately we have to do expansion one more time. This is a little cumbersome, but just in order to tell you the exact algorithm about computation of a determinant. So now let me call this some matrix matrix B, then matrix B's determinant is, okay. Now let me use the first column of matrix B because it has two ones and 1 0. So determinant of B is going to be 1 times C sub 1 1. Let me put the prime here in order to distinguish from the cofactor of a matrix A. And the second 1 times C sub 2 1 prime. Okay. And we don't have to care about the last entry because that is 0. All right, and C sub 1 1 prime is, now we eliminate the first row and first column, then we are left with this 2 by 2, and the computation of 2 by 2 matrices determinant is easy, just do cross product and make difference, compute the difference. Okay. So 38 minus 5, and C sub 2 1 is, now eliminating the second row and first column, then we are left with 2 by 2, 2 9 negative 5 8, and whose determinant is 16 plus 45. And don't forget this sign operator, because subscripts gives us two subscripts give us a now odd number, so we have to change the sign to negative. So 43 minus 61, that is negative 18, right? So matrix B has a determinant of negative 18. Now we go backward, right? So C sub 2 3 is we have two negative signs, so it becomes positive 18. And matrix A's determinant is 4 times 18, which is 72. All right. So the procedure is the same as before. We do Laplace expansion after choosing one row or one column and figuring out the linear combination. But in case of 4 by 4, we have to do Laplace expansion twice because some matrix is going to be 3 by 3. Okay, so that is quite cumbersome, but no one's compute the determinant like this nowadays because we do have computers, right? So just understanding the algorithm behind that, I think that is enough. Okay. So once again, determinant is given by linear combination. So if we choose one row, the linear combination of row vector, and if we choose one column, then determinant is going to be linear combination of column vector. Okay. So from this fact and from this definition, we can establish several properties of determinant. So in lecture slide, we have 5 properties. So let me illustrate one by one. So the first property, let me skip this one for a second because it is related to the third property. Okay? So let me illustrate the second first. If a matrix has a 0 column or row vector, then the determinant should be equal to 0. This is quite obvious, right? Because a matrix has a 0 column, then we can simply choose that column and do Laplace expansion. And the Laplace expansion is going to be 0 because all entries in that column are equal to 0. Okay, so it boils down to 0. Linear combination is going to be 0. Okay. Or, if a matrix has a 0 row vector, then we can choose that row, then its linear combination is also 0. Okay. So the second property is quite obvious. And now let's think about the third one. Determinant of a triangular matrix is simply the product of its diagonal entries. Triangular matrix looks like this. Okay? So all the entries above diagonal are equal to 0, like this. Okay? This is just one type of a triangular matrix. So, this matrix forms a triangle like this. Okay? This is why this is called a triangular matrix. And this is called a lower triangular matrix. And we can think of the opposite. That is a upper triangular matrix. It looks like this. 1, 1, 2, 2, 3, 3. Now the entries below diagonal are equal to 0. So we have 1, 2, 1, 3, and 2, 3. Okay? This is called upper triangular matrix. Okay? And both types have a common property, that is, their determinants are just the product of diagonal entries. Okay? Think about this a lower one. So if we do Laplace expansion by the first row, okay, and the determinant of this matrix is going to be A sub 1, 1 times C sub 1, 1, because we don't have to think about the second and the third entry. Right? And C sub 1, 1, by the way, is A22 times A33. Right? The determinant of this submatrix is just the product of this diagonal. Okay? So total, the determinant of this matrix is the product of these three diagonal entries. For this one, upper triangular matrix, now we do Laplace expansion by the first column. Then it gives us A sub 1, 1 times C sub 1, 1. And C sub 1, 1 is this 2 by 2. Right? So the determinant is A sub 1, 1, 2, 2, 3, 3. And we have the same formula. So whenever we encounter this type of matrix and we are asked to evaluate the determinant, the only thing we have to do is just take a look at the diagonal entries and compute the product. Okay? And so for example, if n least one entry on the diagonal is 0, then the determinant of that matrix is going to be 0 automatically. Think about this example. 1, 0, 7, and we have zeros in this area, and say negative 2, 11, 8, okay? And this is a triangular matrix, okay? So for its determinant, we can just take a look at the diagonals, and the one diagonal entry is 0, so the product is going to be 0, right? So the determinant of this matrix is going to be 0. So this is quite useful and practical property. And furthermore, we can deduce we can derive the first property from this fact. Determinant of identity matrix is equal to 1 because the identity matrix is a triangular matrix. In 3 by 3 case, this is a lower and upper triangular matrix because below diagonal and above diagonal, all entries are equal to 0. Right? So its determinant is going to be product of these three ones that is equal to 1. Okay. So the first property is immediate from the third one. Okay. And the fourth one is also easy to understand because a matrix A and its transpose have the same determinant, meaning that determinant is at least invariant to this matrix operation, transposition. So even though we take a transpose, we have the same determinants. Why that is true? Suppose that for the determinant of original matrix A, we choose row I. Okay? And we do Laplace expansion by that row. Alright? And for transpose, the determinant, we do Laplace expansion by column I. Okay? And by the property of a transposition, row I in the original matrix is the same as column I in the transpose. Okay? So we do have the same expression of Laplace expansions, so same linear combinations, so same determinant. Okay? So the transpose has no impact on the determinant. Okay, that's the first one. And the last property is a non-trivial. It's not that straightforward. Uh, so we are going to prove this fact in the next video. But in this video, let me just introduce that property. That states, suppose we have a matrix A, okay, and the matrix R denotes the low echelon form of this matrix. Okay, and remember the low echelon form transformation. So we studied three types of elementary row operations: row addition, and row switching, and row multiplication. And for transformation, we use this row addition mostly because that is a most important operation in order to transform the given matrix into row echelon form, right? And suppose we obtain low echelon form from matrix A only by way of row addition. So we don't use row switching and we don't use row multiplication. Okay, only by way of row addition we obtain low echelon form. Then original matrix A and its low echelon form have the same determinant. Okay, so the determinant is invariant to enlist this row addition. But if we use row switching once to compute the low echelon form, then the original matrix, the determinant of the original matrix is just the negative of the determinant of low echelon form. Okay? If we use row switching twice, then we have two negative signs. So the original matrix and low echelon form have the same determinant. Okay. Let me do one example regarding this property. So we have this 3 by 3 matrix. Now we evaluate the determinant. So let's transform into low echelon form, in order to use this fact. So first we can begin by switching the first and the second rows because we need, so in the original matrix we have a leading zero in the first row, but the low echelon form does not have leading zero in the first row, so we need to switch first and second row. So then we have 3, 4, 5 and 0, 1, 2 and 6, 7, 8. Okay. And in order to transform into low echelon form, we have to kill this number 6, right? Because a last row must have the largest number of leading zeros, but the second row has already one leading zero, so we have to eliminate this number 6, right? And how to do that? Because we have a 3 in the first row, so multiply by -2 and add it to the last row, then we can kill this number 6. So this process gives us 3, 4, 5, 0, 1, 2, and multiply by -2. So multiply the first row by -2, so -6, -8, -10, and add it to the third row, then 0, -1, and -2, I guess. Right? Okay. And then we have to kill this -1. Okay. So it's just adding the second row. So adding to the second row. So adding the second row to the third one gives us. Now we can kill those two numbers at the same time. Okay. So this is now in low echelon form of the original matrix. Cool. And think about the determinant of this low echelon form, because a last row is going to be out. So it turns out that low echelon form has a 1, 0 row vector. Okay, the last row is just a zero vector, 3 zeros. So by the second property of determinant, if a matrix has a 1, 0 column or row vector, determinant is 0. We don't have to do Laplace expansion. Okay, so we can say the determinant of this matrix, low echelon form, is 0. And we use the row switching once here. Okay, so by this property, the determinant of this matrix is going to be negative of low echelon form's determinant. But low echelon form has 0 determinant. So we can say determinant of this matrix is just a 0. Okay. So this is the way to, so this is how to use this property when we are asked to evaluate the determinant of matrices. Okay. So we can do Laplace expansion, or we can transform the given matrix into low echelon form by way of row addition or row switching. And if we use row switching, the only thing we have to do is just to change the sign from positive to negative. If we use row switching twice, then it becomes a positive because we have two negative signs. If we use row switching 3 times, then back to the negative sign, and so on. Okay? But the row addition itself, so row addition alone doesn't have any effect on the determinant. Okay, so even if we use row addition multiple times, row echelon form and the original matrix have the same determinant. Cool. And the last property leads us to the following theorem. So suppose we have an n by n matrix A, then we have 2 equivalent statements. Okay, this is the bottom line of the lecture slide in the previous week. So the most important one. So now this theorem gives us sufficient and necessary condition for singularity. Okay. It turns out that, so the theorem states that A is a singular if and only if its determinant is equal to 0. Okay? And this if and only if statement provides us necessary and sufficient condition. If statement provides sufficient condition, if it snows a lot, school will be cancelled tomorrow. So the heavy snow is a sufficient condition for the shutdown of the school. Okay? And only if statement gives us a necessary condition. And finally, if and only if statement gives us a necessary and sufficient condition. Okay? And necessary sufficient condition is just equivalent statement. So saying that A is a singular, so matrix A is a singular, is equivalent to saying that determinant of matrix A is equal to 0. Alright? Now we are going to prove this statement because it is important. And the proof is not that difficult. Okay? So for the proof of this equivalent statement, we have to do 2 things. First, we have to show this singularity implies 0 determinant, one direction, and its converse. Now the other way around, 0 determinant implies singularity. Okay? Then these 2 directions imply that these 2 statements are equivalent. Okay? So A implies B, and B implies A too, vice versa. So A and B are equivalent. Alright, so let me first do this direction. First direct, from the left to the right. So suppose that matrix A is a singular. Okay? And remember the definition of a singularity. Okay? It comes from the rank. So when we study the rank of a matrix, we say matrix A has a full rank if the rank of a matrix is the same as the dimension of the matrix. Right? So A is a singular. Singularity implies A has no full rank, right? Meaning that is low echelon firm has at least 1, 0 row vector, right? So in case of an n by n matrix, if low echelon firm has a 1, 0 row vector, then the matrix or the rank of the matrix is going to be n minus 1, so it does not have a full rank, right? So singularity implies low echelon firm has at least 1, 0 row vector. Okay? But by the second property of determinant, if a matrix has a low 0 vector, then its determinant is going to be 0. Because A's determinant is, the plus minus, regardless of the sign. Okay? Echelon form and the matrix A have the same determinant, and if the low echelon form has a 1, 0 row vector, then determinant is going to be 0 by the second property. Okay, so here we use the fifth property, and this comes from the second property. All right, so singularity implies zero determinant. Okay, so now this direction is done. Now let's do the other direction. So now we have to prove that if determinant is 0, then matrix A is a singular. Okay? And for the proof of this statement, let me consider its contrapositive statement. Okay, contrapositive, contrapositive statement. So to illustrate this, think about one conditional statement. So A implies B. If A is true, then B is true. Its contraposition is given by, so we call this B consequence of this statement and A hypothesis. Okay? So it starts with a negation of consequence. So if we negate consequence B, then hypothesis is not true either. So if the consequence is not true, then the hypothesis A is not true either. That is a contrapositive statement. All right? And this is a number one principle in logics or in mathematics. The original conditional statement, and its contrapositive statement are equivalent in the sense that if the original statement is true, then its contrapositive statement is true, and vice versa. If a contrapositive statement is true, then original statement is true as well, All right? So using this fact, we're going to take a contraposition of this statement to make this be, all right? So now its contrapositive is we negate the consequence. So if A is non-singular, then matrix A has a non-zero determinant. Okay, now we are going to prove this. So non-singularity implies full rank, right? A has a full rank. That means its low echelon firm has a no zero row vector, right? So in case of a 3 by 3, if the row echelon form has no zero row vector, then it looks like this: A, B, C, 0, 0, 0, and some entries. right? So we have one leading zero, just one leading zero in the second row, and two leading zeros in the third row. Okay, think about the reason, why this is true. Because we have another non-zero element, say x here. Okay, then we can kill this b using row addition, right? So this is not a row echelon form. Similarly, if we have some non-zero element right here, then this is not a row echelon form either, right? We can kill this number by scalar multiplication or row addition of a first row. So the row echelon form for a non-singular matrix must take this form. What is this? That is a triangular matrix, and the determinant is going to be the product of these three diagonal entries. But A, B, C should be non-zero numbers because if B is a non-zero number, so if B is 0, okay, then this is not an echelon form because we kill this C or X, right? So A, B, C should be a non-zero numbers, so the product of A, B, C, that is the determinant of this matrix. Determinant of this matrix, low echelon form, that is a non-zero number. Okay, so the original matrix and this low echelon form have the same determinant by the last property of determinant. So we just proved that if A is a non-singular, then its determinant should be non-zero number. Alright, so these two statements are equivalent. Alright, so we just established the equivalence between these two. A has full rank, meaning that A is a non-singular, and A has a non-zero determinant. Okay? And if A is invertible, then the system of linear equation, AX equals B,